Kia ora Year 12. This is the third video looking at how to integrate some harder exponential and log problems. So these three are a little bit trickier, and it's just an example of how you have to stop and look hard before you start doing anything. So two of these are pretty okay, and one of them I think I would class as challenging for a secondary school student. So have a look and see which ones you can do without any hints. So pause the video and try them. Okay, hopefully the pattern that you've spotted in this one is that we've got this derivative and function pattern. Okay, so in the numerator we've got the derivative of e to the x plus 1, and we've got exactly the right thing. We don't even have it times by a constant. So that one's going to be fine. And we know that that's going to integrate to give me a natural log. Let's look at the next one. Here, in the denominator, I've got 1 plus e to the power of 2x. So the derivative of that is 2e to the power of 2x. You can see that sitting in the top line. So these first two are probably, I don't know, achieved level 3 questions. They're really not very hard. This last one is interesting. So the thing that I find kind of funny about these three integrals is that when you look at them quickly, it's not that one looks much worse than the other two, right? They all have got e to the power of something in them. But this last one is not very nice. So let's do the first two quickly and then come back to the third integral. So we're going to leave a gap, and it's going to be something times the natural log of the absolute value of e to the x plus 1 plus c. So let's look at that and now work backwards and say, what's the derivative of the inside function? It's e to the power of x. That's exactly what I've got on here. So that's going to be my final answer. Now just to check how that's come about, let's look at if we had y equals the natural log of e to the x plus 1 plus c. Well, the first thing to notice here is that I can drop those absolute value signs because e to the x is always positive, and so e to the x plus 1 is also always positive. dy by dx is going to equal 1 over this, 1 over the blob, times the derivative of the inside function. And when we differentiate the plus c, of course, we get 0. So we end up with exactly what we wanted. Okay, so that's the first one done. Now, if I have to, I can do that using a Au substitution, and I'm going to do that now as well, just so that you're really comfortable with that. So here I'm going to start off by saying let u equal e to the power of x. So du by dx is equal to e to the power of x. du is equal to e to the power of x dx. And what I'm looking for here is to match this up with something directly in the integral. And that's working quite well. So now I can rewrite the integral as du over u plus 1. I would much rather write it out as this, 1 over u plus 1 times du. And now I get back to the natural log of u plus 1 plus c, which is the natural log of e to the x plus 1 plus c. Okay, so that's some pretty basic substitution revision for you as kind of a side effect of solving that problem. We're going to do something similar for the second one now. So the integral of e to the 2x over 1 plus e to the 2x dx is going to equal something times the natural log of 1 plus e to the 2x plus c. But when I differentiate the inside function, working backwards to check my answer, I'm going to get 2e to the 2x. But I don't want that, I've only got 1e to the 2x. So I have to multiply through by 1/2. So my final answer here would be 1/2 times the log of 1 plus e to the 2x plus c. Right, so that's the first two done. Now let's have a look at the next one. it looks pretty innocuous, but the e to the 3x causes some difficulty. So we've got e to the 3x over 1 plus e to the 2x. I'm looking at it and I can see that I haven't got exactly the derivative, or close to the derivative up here, of what I've got going on down here. So I'm going to have to do something to somehow split this up, I think. And I might do a U substitution to see if it helps me think about it. Right, so if I'm desperate, I'm probably going to try either parts or substitution. This just feels to me like it's going to be a substitution one. Okay, so we'll let u equal e to the power of x, which gives me du by dx is equal to e to the x. Du is equal to e to the x times dx. So now I'm going to try and work everything in here into something to do with u. U squared is e to the x squared, which is e to the 2x. So we can get this into a u. Du is equal to e to the x dx. So I'm going to do something to split up the numerator. So here I've got e to the 2x times e to the x dx, because I'm trying to work in the du, over 1 plus u squared in here. So I'm slowly transforming it. Right, now that gives me u squared over 1 plus u squared du. Now, hopefully, I'm starting to see where I can go with this, although it's still a little bit tricky. It would be really good if I had 2u up here, right, because that would be the derivative of this bit here. But I haven't got that. Instead, I've got u squared over 1 plus u squared. Now, the only thing I can think to do here is that we know from A level this year, but not last year. Oh, where's it gone? We know that the integral of 1 over 1 plus u squared du is equal to tan inverse u plus c. So I'm getting pretty desperate now, and I'm going to try and work this into this integral here. So how can I do it? Well, I can add and subtract the same thing. So I'm going to go u squared plus 1 minus 1 over 1 plus u squared du. Let's see if that's going to work. Right, rewriting, I get 1 plus u squared, take away 1, over 1 plus u squared du, and this is starting to look good. So now I've got 1 minus 1 over 1 plus u squared, which integrates to give me u minus, the angle here is tan is u, tan inverse of u, plus c. And u was equal to e to the x. So we've got e to the x minus tan inverse of e to the x plus c. Right, now that was quite full on. So what I want to do is to practice some differentiating by working backwards to check that we get back to where we wanted. So let's start with y equals e to the x minus tan inverse of e to the x plus c, and differentiate. So dy by dx is this, e to the x minus, okay, so straightforward chain rule on this, 1 plus over 1 plus e to the x squared times the derivative of the inside function, which is e to the x. Now we need a common denominator. We're going to have e to the x times 1 plus e to the 2x minus e to the x, which gives me e to the x plus e to the 3x minus e to the x over 1 plus e to the 2x, which is what we wanted. Okay, so there you go. Make sure if you're watching this and you're in 13 MCA that you are completely confident with this basic pattern here. And also remember that you need to know the integral and the derivative for the inverse tan function this year. Thanks for watching. Let me know if you've got any questions on problems similar to this, or if you can't find where to revise them from the Delta book or the Pure Maths book.